And we are going to look at the class A power amplifier and calculation of efficiency both in class A and also in class B and class AB under some idealized assumptions. If you recall, the class A power amplifier circuit, a very simple circuit that was drawn yesterday with integrated circuits in mind, that is, we used the minimum number of resistors and as many transistors as is required. We have a VI plus minus the main transistor Q1, which is operating in the emitter follower mode, that is, the collector is connected directly to plus VCC and this emitter goes directly to the load RL. The voltage here is V0 of t. We have gone back to the time domain, and the current through this is I0 of t. In order to bias the transistor, we use another transistor in the current mirror mode, that is, we use a Q3, whose emitter goes to minus VCC. Emitter goes to minus VCC and the current IQ of Q3 is decided by the main transistor, which is the current deciding transistor, which we had called Q2. Its collector is connected to the base and this is connected to a resistance R1. The current through this is Iref, the reference current, and this naturally has to go to plus VCC. Okay, this is the transistor and the emitter is connected to this emitter. I have shown a simple current source, but it could be a Widler's source depending on what value of IQ you want. If you want very low as compared to Iref, then you use a Widler's source, another resistance here. Okay. Obviously, IQ is approximately equal to Iref. Okay. IQ is approximately equal to Iref. Okay. And this Iref is equal to twice VCC, yes, minus VBE on, which we will use as 0.7 divided by R1. Okay. This is the value of IQ. Now, in order to determine the transfer characteristic of the class A amplifier, that is, transfer characteristic is plot of V0 versus VI. In order to determine that, we take the total currents and total voltages. Let us call this current as I sub total current, capital C1, small I subscript capital C1, if you recall our terminology, I sub C1, and then this voltage, this will change with the applied signal. So, this voltage we no longer call capital V B E, but we call small v B E 1, the total voltage. All right. Then obviously, the relationship is that VI is equal to VBE1 plus V0. Agreed? Let us write this relationship, that is word 1000 words. This relationship, as you will see. V sub I is equal to V sub BE1 plus V0. If you recall, the current versus base emitter voltage characteristic, VBE1 can be written in terms of I sub C1, and the relationship is that this is Vt log of the current IC1. Please be careful about the notation. This is the total current divided by IS1, all right, plus V naught, okay, V naught. And you also notice from the circuit that I sub C1, if we ignore the base current, that is, if we consider beta to be very large compared to unity, which we assume throughout, then I sub C1 is obviously the sum of IQ and I0. Isn't that right? And I0 is obviously V0 divided by RL, and therefore from these observations I can write this as VT, VI equal to VT log of IS1, and this can be written as IQ plus V0 divided by RL plus V0. If you see it carefully, unfortunately, this is my relationship between Vi and V0, and obviously it is a transcendental equation and it can be solved only by iteration. All right, that is, for a particular Vi, you assume a value of V0, see if the right hand side is equal to the left hand side, if not, change it and go ahead doing it till you get a reasonably good approximation between the left hand side and the right hand side. Maybe the difference is of the order of 10 to the minus 4. The error criterion you have to decide yourself. Okay. However, for very large RL, such that V0 by RL can be ignored compared to IQ, we can find an approximate relationship. Okay. So, we consider a case 1, we consider a case in which RL is large. If RL is large, then obviously the relationship is Vi approximately equal to Vt log of IQ divided by IS1, which is a constant now. We approximate this term which varies with V0 by a constant plus V0, and this obviously is VBE1, the DC voltage across the first transistor between the base and emitter, plus V0, which means that V0 is equal to Vi minus 0.7 volt, our usual relationship that we got in class B also. It's the same relationship. Okay. And therefore, for large load where V0 by RL can be ignored compared to the quiescent point current IQ, IQ was established not by load line but by a current mirror. Okay. Now, this relationship obviously is very easy to plot. We shall have a when Vi equal to 0.7, the output voltage is 0. Vi V0. V0 is 0 when Vi equal to 0.7, which means that the characteristic would be something like this. If you have an offset here, this voltage would be 0.7. What would be this voltage? When Vi is 0, this will be minus 0.7. Okay. So, you know these two lines, and then the relationship is V0 equal to Vi minus 0.7. So, the slope would be unity. However, it does not go indefinitely, because the maximum output voltage and the minimum output voltage, they are both limited. What is the maximum that is permitted? VCC minus VCE1 set. There is a reason why I am saying VCE1. Let us look at the circuit. This voltage, the maximum that can happen is in the positive side is plus VCC minus the voltage drop here. On the other hand, on the negative side, the minimum value, when V0 is negative, the minimum value that can occur is minus VCC plus VCE3 set. Is the point clear? Okay. So, we have found out what the minimum is, minus VCC plus VCE3 set. It is therefore important, you see, even with these symmetries, even with this lower limit and upper limit, the swing is not symmetrical because it does not pass through the origin. Don't you see that? But it is class A operation. Class A, why do we refer to class A? In order to reduce the distortion as much as possible. Therefore, we shall never go to saturation, but theoretical limits of the maximum positive swing is VCC minus VCE1 set, your input voltage. What is the input here? Input voltage is this plus 0.7. Similarly, this voltage would be this plus 0.7. Okay. So, you know the input voltages, the input voltage must not exceed these two values, either on the positive side or on the negative side. You must be well within these limits. This figure only shows the limits, okay. You should not operate the transistor so that the peak swing goes here, because then you are asking for distortion. You could as well go to class AB or class B amplifier, okay. Class A amplifier is for low power level and very little distortion, okay. However, if we go back to the relationship, what was the relationship? VI was equal to VT log of, I beg your pardon, VI was equal to VT log of IQ plus V0 divided by RL, that divided by IS1 plus V0. This is our exact relationship, the transcendental. Now, a problem arises when RL is small. When RL is small, the previous case we considered RL large, so that the first term could be approximated by a constant. Then the task was easy. When RL is small and these two terms are comparable to each other, then a problem arises, because when VI is negative, V0 will also be negative. It's an emitter follower after all. V0 will also be negative, and there is a possibility that this term may go to 0 or negative. Is that clear? So, when Vi is less than 0, V0 less than 0, and if V0 is less than or equal to minus IQRL, if V0 less than or equal to minus IQRL, what will happen? This term cannot be found out. Physically, what will happen? Physically, suppose V0, let's consider this point, V0 equal to minus IQRL. Under this condition, this will be 0, log of 0 would be minus infinity, and therefore Vi would be minus infinity, and infinite negative voltage is required. Obviously, this does make sense. There must occur something physically. If we look at this circuit, what will happen? Pardon me? Say it loud, even if you are saying it wrongly. How does it matter? Q1 will cut off. Why? That's a good answer. Why? If I, just a minute. Yes, what was the question?
I couldn't understand that if Vi is negative, how can Vo be negative?
Because it's an emitter follower, basically. Isn't that right? The collector is connected to plus VCC, and therefore whatever voltage appears should appear here, except for this drop. Agreed? Okay. Now, if V0 is equal to minus IQRL, what does it mean? V0 is I0RL, which means that I0 is actually in this direction, and the actual current would be IQ here, right? When V0 is V0 equal to minus IQRL, this must be the direction of the current. Agreed? So, IQ comes like this and flows like this. In other words, nothing flows through Q1. So, Q1 goes into cutoff, not saturation. Q1 goes into cutoff. Saturation, it flows a current. But if it does not give a current, if it doesn't contribute to a current at this junction, means it's cut off. So, physically, much before this inequality starts affecting this circuit, Q1 shall be cut off, which means that if we plot V0 versus Vi, well, we will have a plot like this. I am showing it a straight line. It will not be a straight line, because there is a logarithm involved. It is a transcendental equation, but it is very nearly a straight line, very nearly. It is not exactly a straight line. While the upper limit, the upper limit is still set by VCC minus VCE1 set. The upper limit, the maximum positive voltage, maximum positive value of V0 is still set by this. The maximum negative voltage will be set much before that at the level minus IQ RL. The absolute minimum that is possible is minus VCC, then plus VCE 3 set, that we have already seen. But what happens is before that IQ RL puts Q1 off, and if Q1 is off, then no amplification. All right. Okay. So in the case that RL is small, one has to be careful. The swing in the negative direction would be limited, unless, now this also shows you a design criterion. What should be your design criterion? Design criterion, if you want as large a swing as possible, since IQ RL is limiting your swing, and RL is given, RL is not your choice, RL is known, and therefore you have to design your current mirror such that IQ is approximately equal to VCC minus VCE3 set divided by RL. Do you understand this? You have followed this? This clearly shows, this picture clearly shows a design criteria, that if you want as large a swing as possible, you have to take care of the negative swing. Positive swing will occur automatically because IQ plus V0 by RL, when V0 is positive, there is no problem. But when V0 exceeds minus IQ RL, then obviously Q1 goes into cutoff, and therefore your IQ, a proper design should be, IQ should be approximately equal to VCC minus VCE3 set divided by RL. Then we shall get an approximately equal swing, equal possible swing in the positive as well as negative directions without distortion. It is not that you cannot apply a large input voltage, but its negative swings will be clipped. Your waveform, if it is this situation, and if you have driven the transistor to insanity, which means saturation on the positive side, and beyond saturation, beyond this saturation, beyond cutoff in the negative side, what you will get is your output waveform would be like this. Agreed? Highly distorted, because cutoff at minus IQ RL level. If you want to restore this, obviously you will have to go back and redesign your current mirror such that IQ approximates this. Point clear? Yes. We will have problems on this later to be worked out. Okay, with all these now, let's look at the efficiency that a class A power amplifier can give. Efficiency, as I already told you, is defined as the load power, PL, average load power. The load power will be a function of time, V0t multiplied by I0t. You have to take the average value over one cycle. You are basically asking for undistorted amplification. So one cycle of a sine wave is good enough, divided by the DC power that is supplied by the battery. And as I had told you earlier, this DC power is mostly dissipated in the output transistors, and therefore if you calculate the dissipation in the output transistors, that's good enough. Or the other way is, take the supply and connect an emitter there, a DC emitter, the supply multiplied by the DC emitter, that will be PDC. If you want to emphasize that the power is being dissipated only at the collector, then one sometimes uses the symbol eta C and calls it collector efficiency, which means that the actual efficiency of the amplifier, power efficiency, would be less than the collector efficiency, because in collector efficiency you are not taking care, you are only taking care of collector dissipation, you are not taking care of the other transistors, the current mirror transistors, for example. Okay. In any case, we shall ignore all other transistors. We shall also ignore in our calculation, very conveniently, we shall ignore VCE set. we will assume that VC sat is much less than VCC. It's true in practice, 15 and 0.2, and therefore it can be ignored. That will keep our calculations simple. Now suppose in the class A amplifier, IQRL has been so selected that VOT is equal to VOM, the maximum value, multiplied by sine omega t, and VOM, that is the collector, the transistor has been driven to its maximum possible swing, then VOM would be approximately equal to what? VCC, because we are ignoring VC is set, okay? And therefore, if you have a sinusoidal voltage VCC sine omega t across a load RL, then what is PL? PL is VCC, peak value is VCC, so root mean squared value is VCC by root 2, square of that divided by RL. So it would be VCC squared by 2RL. Agreed? If you are not convinced, you calculate it out. You calculate it out like this: VCC sine omega t whole squared divided by RL is the instantaneous value. Integrate from 0 to capital T is 2 pi by omega, and divide by capital T. This is PL, and you can verify that this is equal to VCC squared divided by 2RL. Now, what is the DC power supplied by the source? The effective source is twice VCC, and the quiescent current is IQ. We are ignoring all base currents, okay? The average current, the DC flowing through Q1, Q3 combination is IQ. So PDC must be twice VCC IQ. Very simply, okay? And therefore, the efficiency eta, which is the ratio of the two, is simply 1/4 VCC by IQ RL. You know, let's multiply this by 100, so 1%. You know that you have to adjust IQ, you have to design IQ such that IQ RL is approximately equal to VCC, VCC minus VCE at 3, but we are ignoring that. And therefore, eta max is only equal to 25%. Maximum efficiency. Therefore, every watt you have to be prepared to supply 3 watts, 4 watts. Every watt of output power, load power, you have to be prepared to supply 4 watts, and 3 watts are wasted. Where? Obviously in the transistors. And these 3 watts you must allow for dissipation of these 3 watts, that is, wherever these output transistors are, either you have to supply a cooling fins, or you have to physically force cool air into them, okay? So that's the story. Class A therefore is very inefficient, and I had told you that class B and class AB is resorted to when you want a higher efficiency. And the reason for higher efficiency in class B or class AB should be clear, that there is no quiescent current, or the quiescent current is very small. You see, VB is kept at 0.7 or minus 0.7 in the PNP, then the transistors are on the onset of conduction. So the Q point, in the absence of a signal, the DC that flows through Q1 and Q2 in the class AB amplifier is very small, and therefore P, the quiescent power dissipation is approximately 0. Power dissipation, however, occurs when there is a signal. Why? Because each transistor conducts only for half the cycle. Each transistor acts as a half wave rectifier, and half wave rectified waveform has a DC, and therefore there is a DC dissipation. And we will show now that this efficiency in class B can be increased to 78.5%. You see the increase is approximately pi by 4, no, it's 4 by pi I think, or pi by 4, yes, pi by 4%. We will see how this comes about. But before that, let us look at the power distribution in class A amplifier. Okay, it is instructive to draw these diagrams. Let us say my VIT is of this form. I am drawing only one cycle, all right, only one cycle. Draw these vertical lines. Suppose this is VIT, then VCE1T would be VCC minus V0T, okay. VCE1T, collector emitter drop, if you recall the circuit, would be VCC minus V0 of T, but V0 is approximately equal to VI if you ignore that VBE1. So, it would be of the form VCC minus, let us say, VIM sin omega t, which means that if this is the level VCC, then to start with VCC minus VIM sin omega t, so to start with it will go negative, agree, and then it will go positive like this. The maximum value here would be VCC plus VIM and the minimum value would be VCC minus VIM. Is the point clear? Okay. It is superimposed on VCC. We are showing that VIM, we are not assuming that VIM is equal to VCC. That means we are assuming that because it is a class A amplifier, it is not driven to the maximum. We will see what happens when it is driven to the maximum. So, the maximum, the minimum that it can come to is 0, and the maximum it can go to twice VCC, agree? That is the absolute maximum possible for VCE1T. Okay. As far as the current is concerned, I sub C1, that will also be sinusoidal. About what value? What is the average value of I sub C1? What is the average value? IQ. IQ, and therefore the current waveform. Now, current waveform, would it follow, would it be like this, in phase with VI or out of phase? Oh, that is very simple. When the input increases, the current increases. When the base drive increases, the current increases. So, it is like this. Sorry, it is sinusoidal. The maximum is IQ plus IM, and what is IM? What is this maximum value? IQ plus VIM divided by RL, agree? V0M is approximately equal to VIM, and the minimum value is IQ minus VIM by RL, alright. My drawings are not very good, but you should take this with a pinch of salt, okay. Then the power PLT, the load power, obviously shall be the multiplication of this, the black waveform and the blue waveform, or you could simply square this and divide by RL, alright. In any case, it would be something like this. It is VCC IQ, this is the maximum value, and around this is the maximum value. You see, it starts from here, VCC and IQ, then it goes down like this, and comes like this. This is the power, which is simply the square of this curve, alright, divided by RL, agree? Now, the power curve PLT can reach a minimum value of 0, that is, I might be able to come, let me use some other color, I might be able to come up to this under what condition? pardon me, VIM is equal to VCC, all right. And under this condition, that is when the class A amplifier is driven to its limits, you can show very simply that I made a mistake. This is not PLT, this is PC1T. This is the power dissipated in the collector, VCE1T multiplied by IC1. Okay, so I made a mistake here. You can show that when the transistor is driven to its limits, then VCE1T is simply VCC 1 minus sine omega t, agreed? VIM becomes equal to VCC multiplied by IQ, then 1 plus sine omega t. The maximum value would be equal to IQ, agreed? When the transistor is driven to its limits, let me look at this. This minimum will come to 0, and that can happen when IM, the maximum, is equal to IQ. Okay, so this is VCC IQ multiplied by 1 minus sine squared omega t, which is cosine squared omega t. And if you take the average value of this PC1, which is PC1T average, if you integrate this with respect to t and divide by capital T, what do you expect? What would be the value? VCC IQ divided by 2. All right. Whereas what we have found out is that the total power supplied PDC is equal to twice VCC IQ. So where are the other components? We have found out the dissipation in C1, in Q1. Dissipation, average dissipation in Q1 is this, VCC IQ by 2. I require another 3 VCC IQ by 2 to be able to get this figure. Where are the others? What does Q3 dissipate? PC3. What does Q3 dissipate? The current is a constant IQ, and the voltage across it is average voltage VCC. Isn't that right? If you look at the circuit, let's go back. I've lost it here. You see the voltage across Q3, the average voltage is VCC. Isn't that right? Because this voltage is a fluctuating sinusoidal voltage. The average value of this voltage is VCC. The current is IQ. The average current is IQ, and therefore the dissipation in Q3 is equal to VCC times IQ. So PC3 is VCC IQ. Now I have been able to get 3 VCC IQ by 2. What about the other one? Load power. That is correct. What I am missing is VCC IQ by 2, which I can write as VCC divided by root 2 multiplied by IQ divided by root 2. This is the RMS value of the load voltage, and this is the RMS value of the load current, and therefore this is equal to the load voltage. And indeed PDC is equal to PL, the load power, plus the power dissipated in the transistor Q1 plus the power dissipated in the transistor Q3, and that checks. This is only to give you a physical picture of how the power is being distributed, distribution of power. Now let's look at briefly at the class B amplifier. If you recall, we will ignore crossover distortion. All right, we will ignore crossover distortion, and we will also ignore VCE set. These are convenient. Yes.
So we find out that the maximum power dissipation 50% is in the transformer Q3 in this case. Transistor.
Transistor Q3, that is correct.
So is there any major implication of this?
Any major implication?
So
Well, it has to be designed to.
could I reduce this by anything?
Yes, there are modifications. But then what you do is you distribute it somewhere else. You see, the point that he is making is that Q3 dissipates VCCIQ. It's double the power dissipation of transistor Q1. But you see, in the worst case, Q1 also has to be prepared to dissipate VCCIQ. But during the operation, transistor Q3, when there is a signal, transistor Q3 dissipates twice the power that transistor Q1 dissipates. In other words, transistor Q3 has to be more robust. This is the implication. Now, what we can do is transistor Q3 can be replaced by 2 in parallel. Then the power is split. Or the circuit can be modified so that this power dissipation is shifted somewhere else, is distributed. Okay, nothing else can be done because class A is class A, and the maximum is 25%. For every 1 load power, you have to be prepared to dissipate 3 watts. It's unfortunate that the main transistor, or fortunate, it can even be fortunate, because the current mirror may be added externally if it goes off, but the main transistor still remains. Well, it's a matter of opinion. But let's look at class B. As I said, we ignore crossover distortion. We also ignore the VCE set. This is for convenience in calculation. This is the transistor Q1. Then we have a transistor Q2, which is a PNP transistor, and this voltage is minus VCC. The power goes from here to RL. This is I0T and this is V0T. Very simple circuit. The 2 bases are connected together and this voltage is VI T. Okay, now to have a picture of what goes on. Okay, let's call this as I sub C1 and this current as I sub C2. Then you know that IC1 will take care of the positive half of the load current and IC2 the negative half of the load current. So if I plot IC1, it would look like this. Okay, these are IC1, whereas IC2 have taken care of the direction. IC2 would be the in-between ones. Is that okay? IC2 are the negative halves, but the directions, IC2 comes like this, so the load current is in the opposite direction. They help the load current to remain sinusoidal. Okay? And I think that's all the picture that we need. Let's go into the calculation. Suppose the V0t is suppose Vm sin omega t. Alright, then I0t would be equal to Vm by RL sin omega t. It's a resistive load, agreed? So PLT would be simply Vm squared sin squared omega t divided by RL, and the load power, which is the average value of PLT, would be simply average value of sin squared omega t is half, so it would be Vm squared by 2RL. We could write this down without going to the average value, because this is simply, if this is the voltage across the resistance RL, the power dissipated is Vm squared by 2RL. Okay. Now, what about the power, DC power supply, PDC? PDC which is equal to small PDC average. Okay, let's see what is small PDCT. When Q1 conducts, what is small PDC? VCC multiplied by the load current, which is Vm by RL sin omega t. Is this point clear? When Q1 conducts, Q2 does not, the drop is VCC, and this is the load current, and this is for 0 less than t less than capital T by 2. And when Q1 does not conduct, Q2 conducts, the power expression, instantaneous power expression is the same. Okay, so this would be T by 2 less than T less than capital T. In other words, the PDC, which is the average value of small PDCT, would be twice the average value of this expression, okay, over half the period, 0 to T by 2. What is the average of sin omega t over half the period? So it would be 2 VCC Vm divided by pi R. Is that clear? The average value of sin omega t over half the period is 1 by pi, and I multiplied by 2. Why? Because there are two half periods. To make one complete period, there are 2 half periods, and therefore I can now find out my efficiency. My efficiency would be PL is Vm squared divided by 2 RL, and PDC is twice VCC Vm divided by pi RL, and this works out to pi by 4 Vm divided by VCC multiplied by 100%. Okay, and you also know that the maximum swing that is possible at the load is VCC. Vm absolute maximum is VCC, therefore eta max is pi by 4, which is 78.6%. That is the major advantage of a class B amplifier. That is, for every watt of power to be dissipated in the load, you will have to be prepared to supply how much? 1 point? Approximately, no, 1 point, it's less than 1.3. 1 minus 0.786. Okay, 214. 1.214, okay, so many watts. This is the major advantage of a class B amplifier. Now, in the subject of power amplifiers, the quality of a power amplifier, whether it is class A, class B or class AB, are determined by 2 parameters. Okay, just like a voltage amplifier, you require AV, AVS, RI and R0. In a power amplifier, the impedances are not of consideration, because impedance, you are basically in most of the power amplifiers, it is a common emitter, common collector or an emitter follower circuit. Emitter follower circuit is characterized by high input impedance and low output impedance. So it's eminently suitable for power amplification, because who is feeding a power amplifier? A voltage amplifier. And who is taking power? A small load, maybe a loudspeaker. Okay, so input and output impedances are of no consideration. What is of consideration is efficiency. How good the power amplifier is depends on how much power you waste, how much power you can deliver to the load, and how much power is delivered by the supply. The other consideration is, other parameter is the so-called THD. All stereo amplifiers have this specification: total harmonic distortion. Total harmonic distortion, and this is defined as follows. It is defined as the square root of power in harmonics divided by total power. Power in harmonics divided by total power. It means what we want across the load is, let us say, a voltage or a current of the form A1 sine of omega 0 t. If omega 0 is your input frequency, this is what we want across the load. Unfortunately, due to excursions, due to large excursions, there comes nonlinearities, and we get, let us say, A2 sine of 2 omega 0 t plus etc. etc. We get the higher harmonics. Harmonics means frequencies are integral multiples of the fundamental frequency, and therefore if this current flows through a load, then it would be square of this multiplied by the load RL. And you know that if you have a sum of currents of different frequencies flowing through a load RL, then the power would be simply the power, average power dissipated due to each component. It is a superposition. In other words, the load power, if this is a current, then it would be A1 squared by 2 multiplied by RL, and the power due to this would be A2 squared by 2 multiplied by RL, and the total power would be the sum of these two. Okay? This can be very easily shown. Can you?
Yes, sir.
Take two terms and show that this is so. So, the total power in harmonics would be proportional to A1 square, I am sorry, what would it be proportional to? A2 squared plus A3 squared plus etc. Whereas the total power in the load would be A1 squared plus A2 squared plus etc. So, THD, total harmonic distortion, would be square root of A2 squared plus A3 squared plus etc. divided by A1 squared plus A2 squared plus A3 squared and so on. Usually, what is our aim? Our aim is to make A2, A3, A4 as small as possible compared to A1. So, A1 is usually much greater than AI, I greater than equal to 2, which means that THD, total harmonic distortion, can be expressed as square root of power in the harmonics divided by A1. That is the amplitude of the fundamental, amplitude or root mean squared value, whatever you want. This is approximate, this is an approximate measure, and this is what is used. People sometimes use a percentage measure, which means that you multiply this by 100 and then use a percentage. Okay? We will stop here. We will, in the Monday class, we will work out problems.